Hey everyone, and welcome to this explainer. Today, we are diving deep into the fundamental principles of shipboard power plant control. We're going to break down the intricate, interlocking systems of a marine power plant, taking you all the way from the core philosophy of redundancy through load sharing and right down into catastrophic network protection. Here is our roadmap for today. We'll hit the redundancy philosophy, frequency and voltage control, load sharing strategies, the power management system, layered protection systems, and we'll wrap it all up with earthing and selectivity. Let's just get right into it. Section 1, the redundancy philosophy. Really, why do we need multiple generators? Think about your car for a second. If you lose the alternator, you are completely stranded on the side of the road, right? But on a properly designed ship, if a generator fails, nobody even notices the lights flicker. And that's because marine plants run multiple diesel generators in parallel on one common bus bar. Redundancy is literally built into the architecture. If one machine suddenly drops off, the others instantly absorb the load to keep the lights on. Moving on to Section 2, frequency and voltage control. The hands on the dials. Because here's the thing, running generators in parallel introduces a massive complication. It is exactly like bolting multiple engines to a single shaft. If they aren't perfectly synced up, they will absolutely destroy each other. For parallel operation to succeed, 3 non-negotiable dials must stay tightly locked at all times: network frequency, network voltage, and precise load sharing. If you get any one of these wrong, the generators stop cooperating and start fighting. So, how do we control them? Well, frequency directly mirrors how fast your engines are spinning in physical reality. To control it, the engine's governor physically drives the fuel rack. It's managing the fuel. Meanwhile, to control the voltage, the automatic voltage regulator, or the AVR, modulates the invisible magnetic excitation current. And this brings us to a really crucial survival mechanism, the 95% knee point rule. If the network frequency drops below 95% of its nominal value, the AVR automatically rolls the voltage reference down. Now, you might be wondering, why do that? Well, if the generator is spinning too slowly, but is still heavily excited trying to prop up the voltage, it will rapidly overheat. So this 95% rule intentionally sacrifices a little bit of voltage just to save the physical machine from burning itself up. All right, Section 3, load sharing strategies. Stopping the fight. Once frequency and voltage are established, we need a rock-solid method to make sure these multiple generators actually share the load. The primary strategy for this is called speed droop control. Droop is incredibly robust because it intentionally lets the engine's speed sag, just slightly, as the load increases. The speed reference dynamically decreases as the load goes up, and the absolute beauty of this system is that it happens locally at each engine. It doesn't need a single communication cable between the governors to work. Now, why is a lack of communication a feature? Compare it to asynchronous control. Asynchronous mode is great because it holds frequency perfectly flat, but it relies completely on an active data link between all the governors. If a comms cable breaks mid-voyage, say from heavy engine vibration, asynchronous control fails instantly. The whole system breaks down. Speed droop survives because every generator operates independently. It's pretty brilliant. Which brings us to Section 4, the power management system, the master regulator. Since droop intentionally allows that steady-state frequency to drift a bit over time, we need a macro solution. Enter the PMS. You can think of the PMS like an orchestra conductor. It doesn't override the droop's second-by-second stability, but it sends these tiny synchronized pulses to all the governors simultaneously to hold the frequency precisely at 50 or 60 hertz. But the PMS is far more than just a metronome. It's the ship's ultimate defense mechanism. It constantly runs an available power algorithm, calculating exactly how much power is left in the budget. If a generator starts to overload, the PMS reacts before a blackout can even begin. It instantly triggers preference trips, it sacrifices non-essential consumers like the air conditioning, and it will even aggressively reduce power to the propulsion drives just to keep that core grid alive. Next up, Section 5, layered protection systems. Preparing for the worst. Because we absolutely have to have fail-safes for when things go catastrophically wrong. Take a look at the massive data density here. A single generator has 12 distinct ways it can fail, from internal cooling leaks to reverse power situations. Meanwhile, the shared bus bar that all those generators feed into has a much narrower set of failure modes, requiring only 4 main protective functions. So let's do a quick knowledge check to see how this layered logic plays out in a real-world crisis. Imagine the crew reports a suspected stator interturn fault. Does the system handle this under generator protection or busbar protection? Any guesses? If you guessed generator protection, you hit the nail on the head. An interturn fault happens deep inside the generator's own internal winding insulation. It's a highly localized failure. And this perfectly explains why the generator requires so many specific internal monitoring functions compared to the much simpler busbar.
All right, our final stretch, Section 6, Earthing and Selectivity, Isolating the Threat.
First, we have to talk about earthing. This is a big one. If you directly earth a generator, a single fault unleashes this uncontrolled, incredibly violent spike of fault current that can just destroy equipment. But on the flip side, if you use a completely isolated network, faults become totally invisible to your sensors. They just hide like ticking time bombs. So marine engineers have to split the difference.
So what's the solution? It's connecting the generator star points to a neutral point resistor, or an NPR. It's a brilliant compromise. Housed in its own cubicle, the NPR deliberately chokes the fault current. It literally gives you the best of both worlds. It prevents those destructive arc flashes while still giving your protection relays a clear, stable signal to read. Now, let's test this concept of selectivity, which is basically the art of tripping the exact right breaker at the exact right time. Let's say a massive earth fault hits the main tie cable between switchboard 1 and switchboard 2. What trips first? This system acts surgically here. It's going to trip those tiebreakers immediately. By doing this, it instantly splits the plant into two completely isolated, independently stable grids. It essentially buys you time to clear the damaged cable without triggering a total blackout on either half of the ship. Only after the plant is split will individual generator breakers trip, and only if the fault is still detected. When you step back and look at it, every single system we've talked about today exists just to solve a problem created by the system before it. Redundancy demands parallel running. Parallel running demands synchronized governors and AVRs. That synchronization requires Droop to share the load. Droop needs the PMS to fix the frequency drift. And that whole web requires surgical protection. It is just a massive, cascading loop, all designed to do one thing: keep those propellers turning. I want to leave you with a bit of a provocative thought to wrap things up. Think about the cumulative nature of fault currents. Every single new machine connected to a busbar adds its own short-circuit power to the total rating. So if you upgrade an older vessel with modern, incredibly powerful generators, you drastically raise the fault current that those older breakers have to survive, which really leaves us to wonder just how close to the absolute thermal and mechanical limit are some of these upgraded vessels truly sailing. Thanks for joining me on this one, and I'll see you in the next explainer.